Hello, chemistry class. It's Mr. Ng with a lesson about chemical equations and how to balance chemical equations. I know the title says stoichiometry, but that's because that's something that we're going to build up to, right? We are going to eventually calculate the amount of chemicals made or consumed in a chemical reaction. But before we get there, let's talk about chemical equations and then how to balance those chemical equations. Please take down good notes because I expect you to learn a lot today. Let's start with a chemical equation. I have an example. Here we have hydrogen gas and oxygen gas react to form water. Here's the hydrogen gas, here's the oxygen gas, and here's the water. In our little mini lab, there's a little box that talks about a word equation. This is what I'm thinking of. This is our word equation. Our word equation talks about what reacts with what gets combined or what mixes with what to make what product, right? And you're going to do it in words. Hydrogen gas and oxygen gas, right? That's in words. And here we have the actual equation. And this says that there's hydrogen gas and oxygen gas reacts to make water. But I think it's going to be more helpful if we draw out these molecules. H2 gas looks like this. Two little blue circles for H's. This is what H2 gas kind of looks like. If you remember, oxygen combines in a double bond, so I'm going to draw two little lines there. And then water has one oxygen and two hydrogens. And I bet some of you noticed something weird. If you remember the conservation of mass, meaning whatever you start with, you have to end up with, notice that we have two blue circles and two red circles, and in the product side, only one red and two blue. That's troublesome, right? That means that we lost an oxygen. So later on in this lesson, I'm going to teach you how to balance this equation. When I say balance this equation, I mean how do we make it so that all the elements in the beginning also show up at the end? And here's what I would do. I would double the water. So here I now have two waters. All right. So now I got two red circles, two red circles. That satisfies the oxygen, but I need four hydrogens, and I only have two here. So I'm just going to double the hydrogen. So now I got two here. And there we go. That's our entire lesson in a nutshell. What's a chemical equation and how do we balance it? How do we make sure that all the elements that are in the beginning also show up at the end? Before we get too far into that complicated stuff, let's go back and let's just talk about the parts of a chemical equation. Here we have the chemical equation that we just balanced, right? And as you can see, the left-hand side is called the reactants. This is like your ingredients, like the oil and milk and eggs for a cake. And then the right-hand side, these things are called products, like the cake itself. On top of that, there are some symbols in a chemical equation. Look, our little plus sign here, that just means these things are added together, right? It's just and. And then our little arrow here, this arrow means produces, right? And later on, we're going to use this mirror as a little dividing line between the reactants and products. And we're going to use this arrow to try to justify the conservation of mass, right? But we'll talk about that in a little bit. FYI, in a little bit, we'll also have arrows that go back and forth. This talks about a reversible reaction where things can go back and forth, like the water turns into the gases and the gases come together to make that water. Probably the most important part of balancing an equation is recognizing the coefficient, these big numbers here. These guys are called coefficients, and they indicate the number of the entire molecule, meaning when I see 2H2, I see 2. This is 1H2, right? This little 2 refers to the fact that there are two H's, right? H's. but 2H2 refers to the fact that there are two of the H2 compound. The coefficient is for the whole compound, and then the subscript is for each element. Same thing here. This 2 says that there are two waters, right? As opposed to this 2, which refers to the two hydrogens. Good. The big number is called a coefficient. This little number, I forgot to write it down. This thing is called the subscript. The last thing that we got to clarify in this chemical equation is these little letters here, these G's and these L's. So a G refers to it being a gas, and an L refers to it being a liquid. So here we have G's and L's, gases and liquids. Oh, and an S is a solid, and sometimes you'll see an AQ for aqueous, meaning something in water, like a thing that's dissolved in water. Good. So we just talked about what a chemical reaction looks like, or what a chemical equation looks like, the little parts of them. Now let's move on to balancing chemical equations. How do we manipulate the coefficients of a chemical reaction to make sure that there's conservation of mass? So let's talk about the conservation of mass, the law of conservation of mass. Simply put, the law says that matter can neither be created or destroyed, and you can only rearrange them, meaning we're not going to destroy an atom, we're just going to replace them or switch them around, right? And here, that means everything you start with, you must end with. Let's just stick with that adage. So let's go to our practice example again. So here we have magnesium and oxygen making magnesium oxide. This is the same lab that we did where we took that little piece of magnesium, we put it over the Bunsen burner, it burned and it made that ash that was a lot heavier. And here I want you to examine this chemical equation. Notice that we start with one magnesium and two oxygens, right? Because of this little subscript, there are two oxygens, right? One magnesium and two oxygens that look like this, right? But notice that in the product side, I only have one magnesium and only one oxygen. That's a problem. We're not ending with what we started with, right? It should be 1 and 2, and not 1 and 1. So here, since we ended up with different numbers of atoms on the left versus the right, we need to fix this. We need to balance this equation. So how do we do this? How do we balance this equation? First, we're going to start by counting the number of atoms on each side of the chemical equation. So here, 1 and 2, 1 and 1, we already did that. And then next, I'm going to try to balance it by adding one coefficient at a time. And here, I think the only one that's goofy is this 2 and this 1. So I'm going to make a coefficient here, and I'm going to write 2 there. I'm going to put a 2 there to double the oxygen just to get at least one thing balanced. So here I added that 2, right? Here, I'll erase this, right? So now I'm going to double that. Good. But it's still not balanced. I'm getting a little bit closer, kinda. One step forward, one step back, or 2 steps forward, 1 step back. Let's keep going here. So now that I have 2 and 2, I gotta get this to have 2 magnesiums. So that seems like a pretty easy thing. All I gotta do is put a 2 here and double that. So if I double that magnesium, I get 2 magnesiums, right, and 2 oxygens. And if you're keeping count, that means that everything is balanced. So here, the very last step, we just kind of make sure that everything is balanced. So here, 2 reds, 2 greens, 2 reds, 2 greens, 2 magnesiums, 2 oxygens, 2 magnesiums, 2 oxygens. Good. That means that law that we started with, the conservation of mass, it's still upheld and we're good to go. That's how we balance the chemical equation. Let's practice some more. Okay, I gave you 2 little practice problems. You could pause the video here and try to do these 2 on your own. Hmm? But if not, I can go through them right now. So here, step one, I'm gonna do a count, right? I got 10, 10 oxygen and hydrogen, SN, oxygen and hydrogen. I got SN, oxygen and hydrogen. And I'm gonna do some counts. I got 2 oxygens, I got 2 hydrogens, and I got 1 tin. I got 1 tin, 1 oxygen, and 2 hydrogens. Oh, that's no good. So I gotta double the oxygens here, right? So I'm just gonna put a 2 here. That doubles both of these things, right? You have to do distributive. So this becomes a 2, and this becomes a 4. That's kind of close. 1, 2, 4, 1, 2, 2. So I just gotta put a 2 in front of this hydrogen, and that makes it into 4. And now I'm done. So I'm just gonna do a final count. 1 tin, 2 oxygens, 4 hydrogens, 1, 2, 4. 1 tin, 4 hydrogens, and 2 oxygens, 1, 2, 4. Good, I am done. Let's do another one. Now in here, if you want to put little ones here, that's cool. If you don't, that's fine too. We know it's a 1. All right, last one. This one's a little bit goofier. If you remember your polyatomic ions, we can save ourselves some time and think of this as just a hydroxide instead of an OH2 separately. So let's do our counts and divide this in half. I got a sodium, I got a hydroxide, I got iron, and I got chlorine. 1 sodium, 1 hydroxide, 1 iron, and 2 chlorines. Again, sodium, hydroxide, iron, and chlorine. I got 1 sodium, 2 hydroxides, 1 iron, and 1 chlorine. Well, well, aren't we in a pickle? So I got 2 hydroxides here, so let's double it here. That means I'm going to have 2 sodiums and 2 hydroxides. Now that I have 2 sodiums here, I only have 1 here. Let's double U here. So this becomes 2 sodiums and 2 chlorines. Oh, I think I'm done. 2, 2, 1, 2. 2, 2, 1, 2. Let's do a final count. 2 sodiums, 2 hydroxides. 2 sodiums, 2 hydroxides. 1 iron and 2 chlorines. 1 iron and 2 chlorines. Hey, I'm done. Hey, thank you guys very much for watching. Please take the time to take down some good notes and write down a strong summary at the end of them. Thank you very much for watching.